I am Shivangi Sharma, MTech final year student of Biotechnology and the host for this session. Today we have Dr. Rishikesh Kulkarni from Indian Institute of Technology, Guwahati as a speaker. He's working as an assistant professor in the Department of Electronics and Electrical Engineering at IIT Guwahati since July 2017. He completed his PhD from the School of Photonics at EPFL Switzerland in 2016. His research interests include digital holography, speckle metrology, interferometry, quantitative phase imaging, speckle imaging, and fringe analysis. Our topic for the talk is digital holographic microscopy for bioimaging applications. Digital holographic microscopy has become a versatile tool in quantitative phase imaging and bioimaging applications due to some of its unique features such as non-contact, non-invasive, and label-free measurement capability. It provides intensity and phase images of the object simultaneously. One of the key features of DHM is autofocusing, which allows accuracy of at focus numerically. This talk will summarize some of the fundamentals of DHM, advantages and limitations, and its applications in bioimaging. Now I request Dr. Rishikesh Kulkarni to enlighten us with his expertise. Over to you, sir.
Thank you, Shivangi, for the introduction. So let me share the screen and can someone please confirm whether the screen is visible?
Yes, sir.
And
Yes,
whether
it
I'm
is
audible?
visible. Yeah, you are audible and visible.
Okay. Okay. So so topic of today's discussion is basically on digital holography microscopy for bioimaging applications. So why this is specifically targeted for bioimaging is because digital holography microscopy also finds a lot of application in material characterization and all. So I will be only discussing applications related to bioimaging and the fundamentals related to holographic microscopy. Uh, Before going into it, let me simply mention the importance of phase in a given signal. So you can treat an image, because we are talking about image you can treat it as a two-dimensional signal, isn't it? So in the case of signal processing, many times the quantity we deal with are amplitude, especially in image. Image is nothing but the amplitude square of a optical wave field, isn't it? So however, we tend to lose, or let's say do not focus more on the importance of phase. So here I have taken one example emphasizing on the importance of phase. So here there are two images. One is of Albert Einstein, one is of Swami Vivekananda. And if you take the Fourier transform of these two images, let's say if I represent it with this quantity, E omega x omega y are the spatial frequency coordinates. E represents the amplitude and phi represents the phase of the Fourier transform. And if you perform inverse Fourier transform, obviously it is expected that you get the same images back, right? However, if you go ahead and simply replace their amplitudes, means amplitude associated with Einstein's image with Swami Vivekananda image and vice versa, but keeping the phase same, I kept the phase same. So the subscript represents E represents for Einstein, V for Vivekananda, and then you perform inverse Fourier transform. What you get is what is shown in the right hand side images. You can clearly see that the quality of the image has degraded. However, you can still make out that this image is of Albert Einstein, this image is of Swami Vivekananda. On the other hand, if you keep the amplitude same for both and interchange their phases, you see, and then perform inverse Fourier transform, you can clearly see here that the images are non-recognizable. Means from the Einstein's image, you get actually image of Swami Vivekananda, whereas in the case of Swami Vivekananda, you get image of Albert Einstein. So this example basically is provided to emphasize the importance of phase in signal processing. Okay, and many times we lose the information of phase, especially in optical imaging cases. So In order to overcome this limitation, in fact, it was you can say a chance discovery. Probably can't call it as a chance discovery. However, Dennis Geber basically invented the technique called holography in 1948, for which he was later awarded with Nobel Prize. Uh, the aim of Dennis Geber was not to basically invent holography. Rather, he was playing around with electron microscope and trying to improve its resolution. And in that process, he basically invented holography. The holography word holo stands for whole. Whole holography means complete imaging. Complete in a sense because our world is three-dimensional. So holography provided the way of capturing 3D images as opposed to 2D images which are obtained in our conventional photography. So the basic difference one must understand is that photography records 2D projection of a 3D scene, whereas holography captures the complete 3D information. Now, in the case of holography, the recording is slightly different in comparison to photography. Plus, there are some additional constraints which are present in holography. There are two steps in holography. One is recording and reconstruction of optical waves scattered by the object. So what we mean by that is whatever you see with your eyes as well as whatever you record with your digital cameras basically are recording the waves scattered from the object. Now, whether the light source is white light source like sun or your tube light, or it is other light sources such as laser and all, whatever is being scattered is being recorded by your camera. So holography also involves recording of the light scattered from the object, and then there is a procedure called reconstruction. Means it reconstruct the optical waves scattered by the object. Means the moment the image was recorded, you can actually reconstruct the same wave using some techniques. We'll discuss that later. So it involves two steps. One is recording and other is reconstruction. And normal photography, which whenever you say about intensity of an image, it is related to amplitude of the wave. So any optical wave, basically you can represent with A into e raised to j phi, where A represents the amplitude of the wave, phi represents the phase. So holography is able to record both amplitude information as well as phase information. On the other hand, your photography basically records amplitude square, that is the intensity. So in the recording of a photograph, phase information is lost. So this is where the advantage of holography comes into picture. And then subsequently we'll see that its application in bioimaging. So holography involves recording of, so how does it record both the information? Remember that no physical device in the world is capable of recording phase. The reason being the phase variations are so rapid in optical wave. If you consider the frequency of optical spectrum, visible spectrum of electromagnetic range, it is so fast that no physical device is capable of responding so fast. There is no electronics developed which can record such fast variations. So basically what holography records is the interference pattern, means intensity of the interference pattern, which is obtained between the light scattered by the object and a reference light. So let me go to the example here, then it will be more clear. So in the case of holography, you require a coherent light source. Coherent light source such as laser source. Means coherent means single wavelength source. Your white light is not single wavelength. It consists of multiple wavelengths from 400 to 700 nanometers. So, but in holography, you require a single wavelength source consisting of wavelength lambda. Okay. So here that's why laser is shown. So when you use laser as a light illumination source, you basically split it into two parts first. The light beam is coming like this, splitting into two parts. This is beam splitter. BS stands for beam splitter. One goes here, other goes here. And this beam is basically illuminating the object. So this is our object. Okay, and this beam is not interacting with the object, is directly falling on the hologram. Okay, directly following so on the hologram. So this is basically photographic plate. So we are discussing classical holography, photographic plate. So I don't know how many of you have seen analog cameras. Okay, in case of analog cameras, we used to have photographic plates, which photographer used to develop the in the lab, and then we used to get the photographs. Not in the case of digital holography, so imaging, where the camera records it and stores it as a array in the computer or in a mobile phone. Not like that. So this is the typical experimental setup associated with classical holography. If you do want to do only photography, this beam will not be present in the photography. Okay, let me write it like this. In the case of photography, this beam is not present. Means this is reference beam, and this whatever is coming is object beam. So what hologram is recording is intensity only, but it is recording not the intensity. So let me write object as O bar e raised to j phi o, and R as, these are two waves. One is object wave, other is reference wave. So as I mentioned, in photography, what you will record is this intensity mod O dash O bar square. Okay, so the phase information is lost, isn't it? But in holography, what you record is mod of O plus R square. Mod of O plus R square, because the two are coming together and the interference is recorded by the hologram. Now in classical holography, once you record the hologram, you take it out and probably do the chemical processing as it is done with analog photography, replace it there again. So it becomes like a transparency for you, like a window, so small transparency through which you can see, but still you cannot make out what the hologram is made up of. But now this is the process known as recording. We have recorded the hologram. Now imagine you remove the object from here. You remove the object from here and then simply in the same setup eliminate the hologram with the reference beam. Again, this is reference beam as it is, and then look through the hologram. You see, as shown in the figure, look through the hologram. What you will see is that as if the object is present, you will see the virtual image of the object. Okay, virtual image of the object. Now, how is it different than photography? It is because if you look at a photograph from any angle, you will see the same thing, isn't it? Why? Because by changing the position, since depth information is not there, object depth information, 3D information is lost, you see the same thing. But in this case, if you look at this from this angle or from this angle like this, you will see different part of the object as if the object is present. So this hologram will act like a window for you. So if you look at the window, a scene outside the window, if you move, the scene will also change, right? Similarly, in this case also it will happen. So this is a basic difference between classical photography, holography and photography. So this was invented way back in 70s after the invention of laser, because when the holography was invented, Dennis Gibber time, laser source were not present. So they became practical when laser source came into picture. However, there is a limitation of application of this in practical scenarios. The reason being the hologram processing and all is very cumbersome, photographic. So that's why nowadays also you don't see any analog cameras. All are mobile based digital cameras and all, isn't it? So though that time has gone where we used to use photographic plates. So then came the uh, uh, invention of digital holography around 1992, where instead of the conventional photographic plate, the scientists replaced this with CCD camera. Okay, so in the place of this, you simply put CCD camera without lens. Okay, there is no lens involved in this. Direct bare sensor is there. So in this case, as you can see, the object is, in this case, this is object. The laser beam is there, split by beam splitter into two beams. One is illuminating the object, other is directly going to the CCD. You see, and the light coming from the object and from the reference beam are interfering at the CCD, and what CCD is recording is a hologram. Okay. Now the difference is here that in the example which I discussed here, we eliminated the hologram in the reconstruction process. We eliminated the hologram and looked through the hologram to see the object. But you cannot do this step. You cannot do this step here because it is CCD is not a photographic plate, right? But, so when you do the recording, so in this case, this is optical recording. Recording is done optically. Similarly here also recording is optical. And the reconstruction means if I want to see the object, it is also optical. I'm using reference beam to illuminate the hologram and see through the hologram to see the object, right? So this is also optical, this is also optical. But in digital holography, optical reconstruction is not possible. Only optical recording is possible. So how do you do the reconstruction then? How do you get the object back? How do you see the object using the recorded hologram? So that requires numerical reconstruction. Okay, numerical reconstruction. So here I have taken a simple example where imagine your object is placed. So recording plane is CCD. I will write it like this. So in this coordinate system, let's say x0, y0 is a plane where you have placed your object. For simplicity, I have taken a point object. Okay, simple point object placed at x0, y0, and I'm considering the CCD plane at z equal to 0 plane. Okay, so this point is kept at x0, y0 minus z0. Z0 is the distance between object plane and CCD plane, that is recording plane. Now here I will record the hologram in the CCD plane. Okay, so you can see that I have represented the object beam which is coming from here and reaching here as O xh yh. Xh yh is the coordinate of hologram plane. So I'm calling CCD plane as hologram plane because it is where we are recording the hologram. So this is nothing but I previously mentioned O bar e raised to j phi O. So phi O is this and O bar is this. Okay, fine. So here it is clear from the figure that this rho 0 represents the Euclidean distance between 2 points. The point on the hologram is represented as xh 0 because it is z equal to 0 plane, xh and this distance. So this is, you can see rho 0 and rho u is in this figure. The light coming from the reference is not shown for simplicity, but as the light is coming from object to the hologram, there is also another light coming from reference, right? So this is rho u. Again, this is a rho u represents the Euclidean distance. So the reference wave is shown here as e raised to j phi r. Okay. Probably you do not basically much focus on these quantities, but just remember that your object and reference are complex waves, means it has amplitude as well as phase. So once they meet, these two meet together in the hologram plane. What your hologram or your CCD is recording is this intensity, intensity of interference of these two beams, as I mentioned before. So this OR, I can represent it like this. O plus R into O plus R conjugate, isn't it? This is nothing but mod O plus R square. So when I expand this, I get four terms: O star, R star, O star, and O star R. What is O star? It's nothing but this intensity of object beam. R star is intensity of reference beam, right? And this is the key feature. You see here in this term there is no phase information. In this term also there is no phase information. But if you look at these two, this becomes O bar R bar e raised to j phi O minus phi r plus O bar R bar e raised to j phi r minus phi O. And if you look at these two terms, it is nothing but mod O bar square plus mod R square plus 2 times O bar R bar cos of phi O minus phi r. You see the difference between the normal photography and holography. Along with the intensity of these two, there is an interference pattern. This is the basically sinusoidal variation which is captured, and you see intensity is become function of phase. Intensity become function of phase. So usually phase of reference is known because it is directly coming from the source, and we are interested to measure the phase of the object. So this is there. So somehow we recorded the information of phase in terms of intensity. Okay, this is the basic factor associated with holography. Holography basically records an interference pattern between object wave and reference wave. Remember, both are obtained from the same light source. This is a very important point one must remember. Both are obtained from the same source by splitting into two parts using the beam splitter. Right? Now, of course, this intensity you to multiply with CCD factor, which is function of exposure time dynamic range. That is simply a matter of a scaling factor. That's all. You can take it as one also. It doesn't matter. Now, very important part one must understand is now if you focus on this part, this is constant. This is constant. What is varying is this quantity which is varying sinusoidally, right? It is a cost term. So it will look like this. Cost term, na? It will look like this. Now, you must have studied about sampling theorem, right, in your signal processing. So the same sampling theorem is applicable in the case of hologram recording, and the maximum sinusoidal frequency it can record is basically depending on the pixel size of the CCD camera. So the CCD should resolve the maximum spatial frequency, means the one I'm drawing here. But remember, this is not temporal frequency. This axis is not time. This axis is spatial x direction variable. Okay, so this is a spatial frequency, and similar to sampling frequency theorem, we know that the sampling frequency should be at least double than that of a maximum frequency present in the signal. So the maximum spatial frequency in present in the interference pattern, if it is fx, f max, then the pixel size, you see here it is shown that f max should be basically limited by the pixel size, which is 1/2 maximum of delta x and delta yh, which are pixels. So you see delta xh and delta yh are size of pixels. So normally with your camera, your mobile camera or your digital cameras, digicam, you have the pixel size ranging from 1 micrometer to 10 micrometers. Okay, 1 micrometer to 10 micrometers. And who decides the maximum frequency, spatial frequency? In this setup, the maximum angle between the object wave and reference wave, this is alpha. I will write it like this. This is alpha. This is the angle. Now, light can come from this point also, from this point also. But what is the maximum angle? It is this. So this alpha max is the maximum angle between the light coming from the object and the light coming from the reference, which are meeting at the hologram plane or CCD plane. So this is f max. So f max should satisfy this criteria and it should satisfy this criteria. So you can clearly see that the size of the object or the angle between the object and reference is basically limited by pixel size. And this is the limitation of digital holography, that you cannot go beyond very large. So it is approximately 1 to 2 degrees. This comes out to be with this value of pixel size. This is few degrees, 1 to 2 or 3 degrees. But with the classical holography, with analog type of holography, this can go to multiple values of degrees. So it can record a larger object in comparison to digital holography. It is suitable for smaller objects. But the advantages of digital holography are so great that nobody nowadays utilizes classical holography. Okay, so with this, then once you record the hologram with the computer, how you need to produce the object again. What do you mean by producing the object? You want to get this thing. And from where you want to get this thing? You want to get this thing from here. Okay, that is the intensity which we call it as hologram H, recorded by the CCD camera. So from H you want to go to this. So for that you need to perform numerical reconstruction, which is based on Rayleigh-Sommerfeld diffraction integral. It may sound very complicated, but if you look at the equation carefully, it is very simple. So what did we do in classical holography? For reconstruction, we eliminated the hologram with reference, right? So you see, first focus on this. You first multiply, because we are doing it in computer. We are performing the physical process using a computer. So you are multiplying your hologram with the reference beam, computer generated reference beam. And then once you do that, what happens here is at this plane, you are computing H into R. Okay, and then you need to, whatever light is produced here with H into R, you want to propagate back to this distance. So this distance is Z0. Okay, ZO. This much distance you want to go. So in this case, we have taken R. So let me say R. R distance I want to travel, because the object was kept at a distance R from the hologram. So how will you calculate the wave propagation? How the wave propagates? So that is basically given by Sommerfeld diffraction integral, which is nothing but we know that each point source act as a secondary source of light. So it will generate secondary waves. All the points will generate secondary waves. And these huge millions of such points, when are getting combined and reach a distance ZR, and in this plane, it will be a very complex pattern generated in this plane, right? All the points will generate spherical waves. They will mix together. You must have seen such points on the water surface also. If you drop 2-3 pebbles in the water, they will generate multiple waves, right? And they will create a complex pattern. Similarly, here it will happen. And this quantity is basically the expression for spherical wave from one point. Then how many points are there? Such hundreds of points are there in the hologram. That's why you are integrating it in the hologram plane, right? So all the points in the hologram plane are considered. Each of them are acting as spherical waves. Amplitude of each of the spherical wave is given by this, and phase is given by this quantity. So what is this rho? Rho is the Euclidean distance between the point in the hologram plane and point in the reconstruction plane, which is similar to the previous one. Okay, so just understand this concept. You need not mug up this equation. If you understand this equation, it is very clear. It might seem complicated, but it is very simple. It is basically based on the principle of spherical, the propagation of wave from a point source. So now, now comes a major difficulty, that theoretically it is fine, but solving it in a computer is not easy. It takes huge time to compute this. So we consider some approximation, where what is approximation? I will not go into details of the equation. I will simply tell about the philosophy of this equation. So what is done is that we assume that the size of the hologram and size of the object is smaller compared to the distance between hologram and the object. Means ZR is much greater than XH and XI and YH and YA. If you consider that approximation, then you further simplify and you come up with an equation of this form. So what did we do? The Euclidean distance is expanded using binomial expansion, and we only consider the first two terms of the binomial expansion of this. So we consider this Euclidean distance. You see, if we consider the binomial expansion of this and consider only two terms, that is what we are saying approximation, then it simplifies the expression to this. And here this is computable. Why? If you look at this part, can someone quickly tell what is this expression stands for? This only focus on this integral. Forget about this part. Forget about this part. Just focus on the integral and this, especially this portion. Does it look like this? What is this? From students, if someone can quickly tell. Sorry?
Fourier transform.
Hello?
Something. Yeah, it looks like Fourier transform, right?
Yeah.
2D Fourier transform.
Fourier transform, right? So you can say that you can simply calculate the optical field in the reconstruction plane where you want to see the object using a Fourier transform. Fourier transform what? H into R into this quantity. That will give, and Fourier transform of the product of this will give you the hologram, the reconstruction. So show you a demonstration. Okay, so first, before MATLAB demonstration, I would like to mention that since we are doing it in computer, right? This integral also need to be solved digitally, right? In discrete manner. So we consider all these quantities in discrete manner. So integration is replaced with summation. So size of the hologram is m cross n. So pixels are considered to be integers, right? So same equation is converted into discrete form. That's all. And again, you have to perform the reconstruction using fast Fourier transform. So it becomes much easier to compute numerically the optical wave field in the reconstruction plane. So let me go back to the original figure here. Now, with depending on the value of alpha, there are two optical configurations associated with holography. So the first one is inline holography, where alpha is 0, means there is no angle between object wave and reference wave. So how do you achieve that? So let's say this is a beam splitter. Light is coming like this. This is your object. Let's say the light is being split into two parts. So this is mirror. This is object. So this is your CCD. So what you are doing here is the laser beam is coming from here, is splitting into two parts. One is going here. Rather, I should have done anyway. So the other is going here, and this is being reflected as it is and going to the CCD. This is my reference, and the one which is falling on the object will get scattered and come here and get combined with R. So O is coming here, R is coming here, which is going to record. Now you see here, both are traveling in the same direction, right? So angle between them is 0. So this configuration is known as inline holography. And when alpha is non-zero, so in this case of inline holography, one can actually use this for particle imaging. So this is basically suitable for particle imaging. So for the sake of completeness, I am discussing this part. For bioimaging applications, you basically use mainly off-axis holography where alpha is non-zero. Okay, so what is that? Let me demonstrate with an example. Uh, so can someone confirm, is the MATLAB screen visible to all?
Yes, sir. Yes, yes,
Okay.
it is available, visible.
Uh, okay, so you see, this is an example of practical hologram. It is recorded by a CCD camera. Uh, if you look at this figure, it looks very random. Looks like it doesn't contain any information. But if you look closely, you see some rings here, right? Some rings are visible. See, so small rings are visible. So this is nothing but caused by the interference of a dust particle, which was present in the air. Even this is the hologram of a dust particle. This is also hologram of a dust particle. So now this represents hologram of multiple such particles. It's slightly different pattern, but the overall pattern is almost random. You can't make out anything out of it. Basically, it was a hologram recorded of in similar to the figure I shown, but the object in this case was a statue of Buddha statue. It was a Buddha statue. Now, during the abstract presentation, we are told that the advantage with holography is that you can reconstruct the hologram at any plane. So if I go back here, uh, uh, in this case, once I record the hologram, I can perform the numerical reconstruction at any distance. Means ZR value can be anything, very close to the hologram, very far from the hologram, at any distance I can do that. But whenever ZR, that is reconstruction distance, is equal to ZO, means the distance at which the object was kept while recording the hologram, when both are same, you will get an object which is at focus. Otherwise, you will see defocused object. Okay, this is the very important advantage, especially in bioimaging, because many of you must have done some experiment with a microscope where you have to use a mechanical knob to bring the glass slide, the samples on the glass slide at focus, right? This is not required in holography. Once you record the hologram, the focusing is done by the computer itself. Okay, so for showing that and for showing the application of off-axis holography, this is the example of hologram I have taken, which I had recorded in off-axis holography setup, where angle between object and reference was non-zero, alpha was non-zero. When I reconstruct it, let me show the reconstruction. So what I'm showing you is a kind of a video where reconstruction is done at different values of Z, and at one or two values of Z, you will see the object very focused, means clear object. Otherwise, you will see a blur object. You see this. Now it is blurred. So you see the Buddha statue is blurred, and slowly you might see that the image is coming at focus, right? And again it is going out of focus. And now it is again become blurred, right? Now one might wonder that why it is showing three parts here. So if you remember our equation, the equation which I shown. So the middle part, very bright part, is showing this thing. So this part is this O mod O square plus R O square, and then there are 2 parts, right? E raised to j phi minus r and e raised to j phi r minus phi 0. So these are the 2 parts. So you get one virtual image and one real image. So either virtual image is in focus or real image is in focus, depending on whether you are choosing ZR equal to Z0 or ZR equal to minus Z0. So if I choose minus Z0, I will show you that demo also. So instead of D, if I choose minus D, then you will see that the other image is at focus. You see here, this is at focus, inverted also, because it is a real image. And you see this is coming in focus and this is blurred, right? So you can treat this as an image of a CCD itself. Okay, you see it is looking like a CCD screen. So this is an example. So let me show you the image, the distance at which it is at focus. You see here, this is completely at focus. You can clearly see the eyebrows which are sharp, right? But at other distance, if I choose wrong distance away from the actual distance, then you will see a blurred image. You see, this is blurred, isn't it? So this is the very important advantage with digital holography. So if there are 2-3 objects placed in the path of the light, you can bring different type objects at focus, right? So this is especially applicable useful in bioimaging applications. Now I will show you one example with inline holography where the setup is like this. Okay, so you see here you might wonder that there is no reference beam, right? There is no reference beam. So the light from the laser is coming directly from falling on the set of particles which are placed, let's say, in a beaker floating around in water, let's say, and whatever is coming out. Now, whatever is coming out here, because particles are so small in size and less in number, that much of the light which is falling on this will go as it is out of the beacon. Only few light rays will be interacting with the particle and coming out. So this part consists of R plus O, both reference plus object. So there is no explicit reference. So you see in this setup, there is no beam splitter used to create reference and object, right? That's why inline holography, uh, if you look at from optical perspective, is more stable in comparison to off-axis holography. Don't need any beam splitter for generating reference and object. And what CCD is going to calculate is record is R plus O square. And you then perform the reconstruction using Z1, you will get the particle images. Okay, so that also I will show that we had recorded, that were recorded rather. So you see these are the particles and they are coming at focus. Okay, at you might see that they are coming at focus and again going out of focus. Now you see that there is some rings which are present, isn't it, around the object, all right, particles, sorry. So these particles, so I have also recorded another image. Yeah, you see same hologram. This is the hologram of polystyrene beads. Each particle is of 90 micron size. Now, if when I reconstructed at 147.5 mm the distance, you see when I zoom in this portion, you see the particle, but it is not focus. But at 149.1, you see it is completely at focus. Very sharp boundary. Again, if I go away from the actual distance, you can get this. So you see, you can find multiple images and there are techniques which can tell that which plane is at focus. So you can say that this plane is at focus by at least looking at it, right? Now, uh, in the case of off-axis holography, you have two further setups which are possible. Uh, like in holography, what did we see? Digital holography, two setups are there. One is inline, other is off axis. Within off axis, we have two type of setups again. One is when the object is transparent, which is usually in bioimaging. Okay. And there are some cases where it is reflective, especially in manufacturing industry where we are studying material characterization. There the samples are reflective. The setup is same. Slight difference is there. You see laser beam is coming. Beam splitter is splitting into two parts. Now this is off axis. Okay, this is off axis. This is also off axis. Two beams. One is going directly here. You can see to the CCD. So this is reference. And this beam is interacting with the sample here. There is a microscope objective which will magnify the image associated with the sample in the field of view, and this is my O, that is objective. And what CCD is going to record is again R plus O mod square. Right. Similarly here, just that you can see the light is not transmitting through the object, but it is directed towards the sample, which is reflecting. So microscope objective, through microscope objective, light is also going and coming back, and then the combination is being recorded by the CCD. Right. Slight difference is there depending on whether the sample object is transparent or reflective. Right. This is the example for digital holographic microscopy. This is a test sample. Okay, though this is known as USF target sample, which is both having amplitude and phase variation. Okay, so you see that this is especially used for understanding the resolution capability of your imaging setup. So you can see the field of view, the total field of view is 200 cross 150 microns, isn't it? So, and the pixel sizes were 1024 cross 768. And when you perform the Fourier transform of this, you get three lobes, 1, 2, 3. So if you remember, I told this is mod O square plus mod R square. Right now, this is with e raised to j phi r minus phi o. This is e raised to j phi o minus phi r. These three lobes are there. Any DHM setup you go, you will see these three lobes in the case of off-axis holography. So you see this is portion is shown in a zoom in fashion. So you see this is a pattern, right? This pattern shows the cosine pattern of intensity, sinusoidal pattern. We derived no cos part. So it is showing this part. And when you do the Fourier transform, you get three lobes, but only one of them is sufficient. This is not required for us. Both of them are carrying the same information. If I filter this part and perform inverse Fourier transform, I will get amplitude image as well as phase image of the object. So this is amplitude image, this is a phase image. So what does amplitude image tell? Amplitude image tell that what is the absorbance of the point. So at each point, let's say in this point, the absorbance was this much, and what is the height or thickness of the sample? This is basically decided by phase. So phase is also not only giving the absorption property of the sample, but also it is giving the thickness of the sample. So this is very important, especially from bioimaging applications where many samples are transparent in nature. So amplitude will not show anything because they're transparent, isn't it? But their refractive index are different. And once refractive index are different, the change in the refractive index will bring change in phase, not in amplitude. So when you see the change in phase, the only image you can with which you can measure or image the sample is with phase image, right? That's why holography is capable of providing amplitude as well as phase image. Another example is shown here of onion cells. You see, so this is a hologram of onion cell. Again, if you look at the Fourier transform, you have three lobes, one here, and other here. Same process you do. You see, procedure is exactly same. Simply take out this portion, perform inverse Fourier transform. You get this as amplitude image, which is similar to what you get in your fluorescence microscopy. And this is the phase image. You see, now this phase image is in a wrap form. Wrapped means this, that let me quickly mention that what you have got is O bar e raised to j phi O. Now, if you want to get phi O, what do? You perform angle operation on this complex quantity O. Argument of O, you will get phi O, right? But the problem with this expression is that e raised to j phi O is equal to e raised to j phi O plus k into 2 pi, where k is an integer, right? Why? Because e raised to j k into 2 pi is always 1. So you don't know. So that's why this operation will give you the phase value in the range of minus pi to pi only. That's why it is shown here in a wrap form. So it is like this. In a clock, when you count the number of rotation made by the minute arm, let's say if you try to count, after every hour it will come back to the same position, right? So what is the angle it has made? If you want to calculate, you have to calculate not only the angle made at a given instant, but also you need to know how many rotations it has made, right? So then you will calculate the total angle. Similarly here, because it is coming back in the range from minus pi to pi again and again, because of this property, you will get this phase. So where you see from this region to this region, there is this part which is there, right? So which is indicating a jump of 2 pi or jump of minus 2 pi. So you have to remove this and bring to this value. So this is unwrap phase. This is wrap phase, and this process is known as phase unwrapping, which is very important in digital holographic microscopy. Okay. And if you look at it in 3D in color, you will see the 3D view of the onion cell. So this provides the information about the refractive index and thickness of the onion cell, which is only possible in digital holographic microscopy, by the way. So because fluorescence microscopy can give you only this part. Now this is the example of again wrap phase recorded by our partners in digital holographic microscopy, and we applied our own algorithm to perform the phase unwrapping, and you can see that this range is from minus pi to pi, but this range is from 0 to around 80. This is phase unwrapped, this is phase wrapped. Okay, from here to here is known as phase unwrapping, which is very critical in digital holographic microscopy. So again, you see this is so complicated. So this is after unwrapping, you get this. This is again onion cells. Both are onion cells examples. Now, this is an example of DHM applied for imaging paramecium cell. Okay, so this is a single hologram which is being captured, and if you record such number of holograms and probably reconstruct the holographic images. So I have shown only one image, no, after reconstruction. But as I mentioned, you go on changing Z. For each Z, you will get different image, right? So that then I will show you a video here. This is a video of a phase map of a paramecium moving around in a sample. You see, this is a paramecium cell which is moving around, and you see another cell here coming in, right? So you can probably make a movie. So it is DHM is very much suitable for 4D imaging. Okay. Now these are again few examples which are provided in the literature, where many different scientists have utilized DHM for bioimaging applications. So this is one example of a resolution target similar to the one I shown you before, the vertical bars and all. So here you see this. If I plot along this line, it will look like this, right? So this height variation they could measure is around 50 nanometers. Okay, so this is and it is validated with the standard values, which is correct. Now these cells in B are the ovarian cancer cells, and the field of view was 60 cross 60 microns, and the number of pixels used to represent this was 404 microns, 404 into 404 pixels, right? And again, this is also an example of ovarian cell. This is red blood cell. These are red blood cells, and in fact, DHM is capable of measuring the shape of the morphological parameters associated with red blood cells, and one can basically come up with the diagnosis associated with the blood sample based on the morphological parameters obtained from DHM. Again, this is a cheek epithelial cell. This is again a quartz crystal from sand. So you can see so many variety of samples are one can measure or one can image using digital holographic microscopy, and importantly, you are imaging it quantitatively. Means you can know the value of thickness or refractive index, right? It is simply not an image. You are actually getting it in quantitative manner. Again, these are the example. Nowadays, DHM has also been used for studying marine bioscience applications. Okay, so these are the plankton. This is an example of hologram of a plankton, which is recorded by underwater DHM. So one of the group have developed an underwater digital holographic microscope which can go down, deep down, do the imaging there, and once you get the image, these are the holograms. When you reconstruct, you see this is a nice image of a diatom plankton. Similarly, another example is this of a copod, where it is after reconstruction it looks like this, right? So this is another example of digital holographic microscopy. One people, many scientists are targeting. And for some of you who are probably working in cell studies, DHM has also been employed for cell morphological studies, as I mentioned, red blood cells and all, and they are being subjected for studying the cell behavior for the changes in them depending on the treatment, drug treatment, and then or by environmental factors such as temperature change or pH change and all. Okay, so these parameters do change the morphology of a cell, and since DHM is capable of providing morphology information, one can utilize it for these studies. And then nerve cell studies also, that how the cell growth is occurring and signaling mechanism, it is also possible. And remember, in all these cell studies, you don't have to do any staining operation. It is label free imaging. So due to label free, you are not destructing the sample, so it is non-destructive. It is non-contact because you are using light as a probing medium. It is non-contact, non-destructive, and it is label free, right? So you can actually do live imaging. Live imaging is very important advantage associated with DHM. And then stem cell studies. So stem cell monitoring, sensing, and identification of them is being conducted, and other applications are also there, like cell growth. And because cell growth and all, if you want, you have to study in live manner, that is being possible with DHM. Okay, so all these applications are available associated with DHM. Okay, so apart from this, I had okay, fine. Uh, one more important thing, one interesting thing, if you are interested to know, is this very interesting thing. I just closed down my discussion for today. Uh, can you observe a bright spot here in the dark circle of particle? Is it visible to all, or is it only visible to me?
It is visible. It is visible.
Yeah, right. So this is known as Poisson spot. This is known as Poisson spot. Basically, when Fresnel, whose equations we are using for calculating the numerical reconstruction, basically presented his thesis that light is a wave of wave nature, and this is what you get. Then the committee member actually ridiculed him, saying that with your theory, you are saying that if you place an opaque object in front of the light source, after a distance you will see a bright spot. Okay, this is what his mathematical theory said. But then when the experiments were conducted, then scientists actually observed a bright spot behind a opaque surface, and this actually practically proved the wave theory of light. So this is also present here. You see the particles are opaque, okay, but still you see a bright spot in between. This is due to the wave theory of light. Okay, so with this I close today's discussion, and I hope I could convey some important aspect associated with digital holography. Thank you.
Okay, thank you, Professor Rishi. Actually, you gave in detail like what is the math behind if you want to see any 3D object, okay, in the digital holography. So that you gave in detail information how it is generally, okay. What is the math behind that is happening and other things, okay. That's really wonderful. If I'm not wrong, like the only the those the participant, if they have some mathematical background, they clearly understand like the how the mathematics is there, and what is the like the 3D shape of the object, any object, how we can visualize it, okay. But I'm not sure about like the other biology and other students, like the participants, how they are and where they are. Now it is welcome to from everyone. Like if you have some like the doubts and if you have some questions, please feel free to ask Professor Rishikesh Kulkarni. And yeah, now the platform is open for questions. Mm. Okay, okay, Rishi. I think I have like the one or two questions might be. So suppose when we are like the looking for so you talked about like the reflection mode digital holographic microscope, right? Where you have like the micro objective is like the focusing an object, and the reflected wavefront is reaching to the camera through the beam splitter, right? So here that is the object wave propagation, right? So so generally when we are having some discussions, so they used to say that if the object wave is like the following through like the micro objective, so and then the reference wave supposed to be also follows through the like the micro objective only,
Yes, yes,
right?
yes,
To match the like the
yes.
path
Phase,
and
yes.
like other things. So here in this like the reflective mode digital holographic microscopy objective setup, like I didn't find that the micro objective additional micro objective, but you
Yeah,
have
yeah,
wondedly
it is
didn't show or like that it is
correct.
there.
Yeah, actually, you can include it and you can exclude it also, because
Uh-huh.
the effect of microscope objective can also be compensated numerically.
Okay,
So the
okay, okay.
contribution of you can remove it by applying some signal processing algorithm such as principal component analysis and all. It is easy to remove. It is the techniques are already there. State of the art techniques are there. Yeah,
Okay,
so it need
okay.
not include. Yeah.
Okay, okay. So, and one more thing, like when we go for the lens-free holography, right?
Huh.
Lens-free holography and maybe inline holography. Is there any like the difference in these two, or like the both are the same?
Uh, in the lens-free case, we don't use any magnifying lens such as microscope objective for imaging
Yes,
applications.
yes, yes.
Whereas inline also, so you can say lens-free holography is a sub-part of inline holography. You can do
Okay.
inline holography with lens also, without lens also.
Okay.
Yes.
And one more thing, like suppose when we are like trying to, so as we came to know that from the other speakers that like when we are going through with off-axis holography, so we are somewhere like what is the area of interest where we have like the imaging area, it is limited with like the certain part only. For
Yes.
example,
Yes.
as you mentioned that
Yes.
object like the object virtual image and real image and the DC part. Okay. And coming to the this inline holography, we are not going to lose anything. So but as we know, the mathematical the algorithm, whatever we supposed to add for the signal processing. Okay. At what cost it is nullifier that like how we can manage, like the competition will be very high or the
No, no,
low
no,
or
not
it
that
is
much. Not that
no,
much. Not that much.
not that.
Especially for particle imaging,
Uh-huh.
it is not that much. That's why for particle imaging, nobody goes for off-axis. Everybody
Okay.
goes for inline only. Uh, Even though image qualities are poorer in comparison to off-axis, but the
Mhm.
advantages are of experimental stability and
Mhm.
signal processing algorithms are developed very well to overcome those limitations. But
Okay.
for biosamples, I have already, with whatever I have seen, uh, the major choice is off-axis only,
Okay.
not in line.
So,
Yes.
and one more thing, like the one Deblu Sahu, he asked how to find out the thickness of sample through DHL. He said,
Yeah. So
like
once
maybe
you
he
know the
might be asking about the profile.
Yeah, so basically, once you know the phase
Mhm.
map comes due to the combination of refractive index and thickness. Okay, it is a function of product of refractive index and thickness. If you know the refractive index, you can calculate thickness, and if you know the thickness, you can calculate refractive index. But if you don't know both, then it is not possible. You
Okay.
have to know one thing. So if you are interested in thickness, you need to have the knowledge about the refractive index of the sample. So from the
Okay.
phase you
Suppose
can
for
calculate the thickness.
uh-huh.
Yeah.
So it is nothing but like the suppose you have some like the sample, and that sample what kind of the refractive index it has that we know,
Yes. Yes.
then only we will get to the information.
Thickness. Yes. Yes. And that is
Okay.
what is done with the red blood cell imaging. They
Oh,
assume some known value of refractive index of a red blood cell sample, and they
mhm.
calculate the thickness.
Okay.
Yes.
So what is the range of like that refractive index of these red blood cells? Since they are in hemoglobin, and I'm not sure about that, like whether they are, I
So there
think
are,
they
I
are
think,
not transparent.
there are some biological terms like erythrocyte or something. I don't know. Depending on that, also the refractive index varies. Probably
Uh,
bioscience people
hemoglobin,
might be
hemoglobin
might be
content,
able to
which
tell.
has, yeah.
Yeah. Like yeah, the
Okay.
biological name, binomial neighbors. I have. I don't know. Yeah,
Yes, I know that. Okay,
yeah,
okay. Thank you, Rishi, for
yeah.
like a wonderful talk. And
Thank you.
if there is no more questions, then Shivangi, please, you can conclude the meeting and thank the speaker.
Yes, sir. On the behalf of everyone, I want to express my paramount gratitude for taking time out of your busy and hectic day to attend the workshop as a speaker on digital holographic microscopic for bioimaging applications. It was thoroughly enlightening and informative session for the listener. Thank you, sir.